Right. Now consider a situation like this. Assume there is a hemispherical surface. It's like an inverted bowl. Okay. Assume the radius of that surface is r. It's inverted and it's fixed. Okay. It's a curved surface, fixed curved surface. Let's say there is a ball placed exactly at the top. Okay. Small object. You can ignore the size of the ball compared to the radius of the hemisphere. Tell me, if we place it exactly at the top and release, what will happen? If it is placed exactly at the top and released, what will happen to it?
It will drop down.
Why?
So because of gravity.
But the surface is there to support it, no?
Oh, the surface is there. Then it'll roll down.
Can't it stay there? Aishwarya, what do you think? Can it stay there?
I think it depends upon the size.
Depends upon the
Size, the shape.
It's a perfect sphere, or you can think of it as a single particle itself, but it has some mass. Okay, it's not massless, it has mass. It's placed exactly at the top of the surface, topmost point. What will happen to it?
So if it's really small, it might stay there, or it might roll down on any of the sides.
Okay, see, it's a question of what happens or how an object moves. I told you all, generally, if you want to decide what happens to a system or an object, the first thing you consider are the forces acting on it. Okay. See, you should not forget this. If you are ever asked what happens to a system, first look at the forces acting on the system. Okay. One of you tell me what forces act on the particle when it is placed there. Assume the surface is smooth. Perfectly smooth. What forces act on the particle?
So the weight of the body.
Weight of the object will act. Weight always acts vertically downward, mg. What else?
Normal force.
In which direction does normal force act? Generally, in normal force, what does the word normal mean?
It's normally opposite to the weight.
Okay, but what does the word normal mean?
90 degrees, sir.
Perpendicular, 90 degrees, correct. So it should act perpendicular to the surface of contact. Exactly at the topmost point, the surface will be horizontal, parallel to the ground. So normal force will be acting perpendicular to the ground, means in the vertically upward direction like this. So there's one force acting upward and one force acting downward, exactly upward and downward. Is there anything acting to the side? Or will any of these two forces have a component horizontally to make it move to the right or to the left? So now you consider it once again and tell me what will happen to the object, the ball, if it is exactly placed at the top. If you still feel it will roll down or slide down, you tell me to which side it will slide, right side or left side?
Sir, it has to stay in the same.
It will stay there itself. None of these forces has a horizontal component to make it move to the side. Okay, so if you leave it exactly at the top, it stays there. In a real life situation, you may not be able to balance it perfectly because real life surfaces are not perfectly smooth. and they're not perfectly spherical or hemispherical. Okay, a little bit of like some ridges and grooves will definitely be there in real life surfaces. That's why in real life it becomes very difficult to balance it, but it's possible. Okay, fine. Now, at the topmost point, these are the forces acting on it. Imagine you disturb the particle slightly. If the particle is slightly disturbed and released. Understand this carefully. You'll find this statement in many questions, slightly disturbed. Slightly disturbed means we give it a small velocity, okay, just enough to make it move from there. So initial velocity, it's not equal to 0, but tends to 0. Okay, almost equal to 0, you can say. So almost equal to or approximately equal to is represented by this symbol. So let's say initial velocity is close to 0 and it is given to the right. Now, Rishi, you tell me what will happen to this particle?
When it's slightly disturbed and released.
Yes.
It depends on where the force is acting.
See, we have disturbed it, means we have given it a small velocity. And then the particle is on its own. What will happen?
So it'll go towards the right side.
Huh. So you are saying it will slide down.
Yes, sir.
Okay. Aishwarya, are you convinced with this? Will it now slide down to the right or not?
Yes, sir.
It will. Correct. Now answer this. You know that if it is slightly disturbed, it will start sliding to the right. Now I'll give you some options, or two options actually. Will it slide down along this surface all the way to the bottommost point like this? Or will it slide along the surface up to a certain distance? Like, will it slide along the surface up to a certain distance and lose contact with the surface and fall like this? Which of these do you think will happen? Case 1 or case 2? Pawan, good evening. You just joined. So this is the first question we are discussing. There is a hemispherical bowl-like surface on top of which there's a particle. If we slightly disturb the particle and release, what happens is what we are discussing. So one of you tell me, if it is slightly disturbed and released, we know it will come down. Will it come down completely along the spherical surface itself and hit the ground, like following the blue path? Or will it slide along the surface only up to a certain distance and then lose contact with it? What do you think will happen? Which case is going to happen?
So case 2.
Case 2. Okay, that's correct. But Aishwarya, can you justify why or how do you say that it will be case 2? Think about it. Rishi, what are your thoughts on it?
Sir, I think it's case 2.
Okay, can you justify why it cannot follow along? It cannot follow the surface.
Sir, because like normally when there's like something, if there's like a thread or something in like holding it back, then it'll have to follow the path of the circumference of the circle.
Okay, since there's nothing to hold it back, you are saying it will lose contact.
Yeah, there'll be like a slide, not very much, but like little towards the end.
Possible. Okay. Aishwarya, any other explanation?
So like if it's in the middle of the path and then if you divide the velocity into vectors, it will follow the x component and then use the path.
Okay, okay, kind of. Very good. I like this way of explaining. See, consider the blue path. Okay. For the object to move along the blue path, what should happen is its final velocity should be vertically downward like this. Isn't it? The surface is becoming vertical. It's exactly a hemisphere. So at the point where the surface touches the ground, the surface is vertical. Means the velocity of the ball will have to become vertical, ball or particle. But see, along the way, maybe at some position here, the velocity of the particle would be like this. It has an x component and a y component. X component is taking it to the right side, y component is bringing it down. Let it be. And along the way, if you visualize the forces acting on it, there will be a normal force acting like this. Normal force should act perpendicular to the surface of contact. So it acts like this. And there will be mg acting vertically downward. Okay. Now you consider normal force and mg acting vertically downward like this. Do any of them have a component to the left? They don't. Normal force has a component to the right. That is what is generating this component of velocity, the x component of velocity in the object. Okay. The normal forces component to the right is giving Vx to the object. Gravity is giving Vy. Okay. Not just gravity. Gravity minus the vertical component of normal is giving it this y component. Okay. There's no force acting on it to the left. If there's no force acting on it to the left, there's nothing to remove this x component of velocity. Then finally, how can the ball have only the y component? That's impossible. So that rightward velocity that it attains will be there with the ball. It can only increase, it cannot decrease. Due to normal forces component, it can only increase. Therefore, it's impossible for the ball to follow the hemispherical path till it touches the ground. It will have to lose contact somewhere. Okay, are you all convinced with this or not? Any doubts? Okay, so after sliding down by some distance, when the speed becomes too much, the ball cannot stay on the circular path. It will have to lose contact with it. So the question now is to find out where the ball loses contact with the surface. Okay, I'll tell you the problem properly. At the topmost position, the ball is just slightly disturbed, means its initial velocity is almost equal to 0. It is disturbed from that position. And we know that it follows this curved path up to a certain extent. And at some point, means at some angle or at some height, it loses contact with the curved surface. After that, it falls off like this. Okay. You have to find out the exact angle where it loses contact with the surface. Let's take the angle with the vertical. So that's the question. How much is the angle when the particle or ball loses contact with the surface? Okay. Think about it, all of you. Come up with some ideas first. How are you going to solve this? And remember, we are in the chapter work energy power, and we have techniques like work kinetic energy theorem, mechanical energy conservation. Okay. And you know that you can see that this is following a curved path. Whenever an object follows a curved path, you can apply concepts of centripetal force, tangential force, those things. Okay. So try to put all these together and come up with an idea to find out where the particle loses contact with the surface. Any answer? The particle loses contact with the surface somewhere. How to frame equations out of it? How to make this statement mathematical? Or how to write a physics equation based on this?
Normal force equal to 0, sir.
Good, very good. Okay. Wherever the ball is about to lose contact with the surface, the normal force becomes 0. Okay, that is how you frame an equation out of the simple fact that something is going to lose contact. Okay, so now the question changes to what is the theta, what is the angle at which normal force becomes 0? Now, what approach will you take to find out that angle? You want to find the angle where normal force becomes 0. So what can be done?
Sir, n minus mg cos theta equal to mv square by r.
Okay, you want to write the equation for centripetal force. Good. Okay. Fine. So we want to find, see, the question now is to calculate the angle theta where the normal force becomes 0. So effectively what you now need to do is derive normal force as a function of theta. And then you put n0 in it, you will get theta. And to derive normal force as a function of theta, the procedure we are going to use is somewhat similar to how we derived tension as a function of theta in this case. Where is that tension equation? This one. Okay. Basically, motion in a vertical circle, whatever we discussed till now, it was all done from the bottommost position. All the derivations were done by taking the object initially at the bottommost position. When it moves from here to here, we know how to derive tension in the string. Now you have to do it in that case. Just recollect what all we did here. To derive tension equation, tension is acting towards the center of the circle. So we had to write centripetal force equation. Okay. And when we do that, when you write tension equation, or when you involve tension in the centripetal force equation, you get the v square term. Theta will be there. V square will also be there. Both are variables. Speed keeps changing. Angle also keeps changing. Now you have to remove one of the variables. And for that, we use energy conservation. We replace v square with this whole thing. But that is for this case, when the particle is pushed from the bottommost position. Now we have to use the same ideas, but apply it to that case. Okay. So start doing this, all of you. Assume like initial velocity is almost equal to 0. You can take it as 0. When it comes to this position, derive an expression for its velocity first. How will you do that? You know velocity at one position is 0. You need velocity at another position. So arrangement is changing and the question is asking you to find out the speed. So you can use mechanical energy conservation or work energy theorem to derive V. Once you derive V, what we do is, see, mg will be acting this way. Now, if that angle is theta, this angle is also theta, then mg cos theta will be acting towards the center like this, a component of mg cos theta, and normal force will be acting like this. So what we are going to do is centripetal force. Can one of you tell me what is the definition of centripetal force? Or what do we mean by centripetal? I'm not asking for the formula. What do we mean by centripetal force?
So it makes the body move in a curved path.
Okay. But what does the word centripetal mean? What you said is also
towards the center.
Towards the center.
It's like towards.
Correct. So basically, centripetal force is the net force acting towards the center. In this case, the centripetal force becomes Net force towards the center means force acting towards the center minus the force acting away from the center. And you will equate that to mv square by r. So this is how you relate normal force to the angle theta. But if you want to write normal force exclusively in terms of theta, you have to eliminate this other variable v. And for that, we use energy conservation. Ui plus ki is equal to uf plus kf. So using these two equations, you can derive normal force as a function of the angle theta. And then in that equation, once you derive normal as a function of theta, substitute normal force as 0 and get theta from there. Okay. Do you think you'll be able to do this or not? Like, I don't want to solve the complete question now. I'll give this to you as homework. But do you think you'll be able to apply these equations and solve it or not? Pawan, can you do this? Aishwarya, will you be able to solve? I didn't get in.
Yes, sir.
Okay. So try this once. What I want you all to do is first go through the tension derivation that we did in case of string and a bob. You observe how we applied mechanical energy conservation in that case and all. Use the same ideas here. You will be able to solve. Okay. So solve this question and send me the solution later. Next problem. Suppose there is a tube like this. Just a moment. Let me make this a tube. The width of the tube is negligible. It's a narrow tube. Compared to its radius, the width is negligible. Assume there's a particle in this tube at the bottommost position like this. It's a smooth tube. Radius is r. Particle mass, you can take it as m. Let's say it's at the bottommost position. I'll directly give you the question. The tube is fixed. Okay. Particle is movable. Find out the speed that the particle must be given, or find out the minimum speed that the particle must be given at the lowest point such that it completes the circle. Okay, think about it. Or solve this problem, all of you. I'll give you 2-3 minutes. Any answer, anyone? The minimum speed such that it completes the circle. It's a smooth tube. Or can any of you tell me an idea? Why should there be a minimum speed? Like, what happens if you give very less speed?
There it'll start rolling back. It'll go.
It will ascend only up to a certain extent, and then it becomes too slow. It won't be able to ascend any further. It will come back. So it will kind of oscillate somewhere in the lower half of the circle. Correct. So you need to provide a certain minimum amount of speed for it to get to the top. Okay. We know where the ball is supposed to go. It's supposed to go to this position. All we have to find out is how to send it there. So let's call the initial position as A, final position as B. If you give the bare minimum required velocity to get there, can you tell anything about what happens to the ball when it gets here? If you give just the sufficient amount of velocity, what will happen?
There will be enough for it to come back to the initial position. Because it has to go down, right?
But what can you say about the ball when it gets here? After that, it will anyway come down. Okay. But we need an equation, and we need an equation which involves speeds.
So will the velocity be nearing zero?
You tell me, do you think so or not?
Yeah, sir, because at one point it slows down and then starts again because it has to go down.
Correct, correct. So basically, this case is slightly different from what we have been discussing in the last two classes and even this one before this. Here, the ball has no chance of falling into the circle because it's in a tube. There's an outer wall and there's an inner wall also. So even if the ball becomes too slow in the upper half of the circle, it's not going to fall into the circle like this or like this. Okay, it will come back along the tube itself. So you have to imagine, if we give it a small velocity, it will go maybe till here. As it ascends, the speed will decrease. So it will stop and come back. Give it some more velocity. It will ascend a little further, slows down, slows down, slows down, stops, and then comes back. Without stopping, it cannot come back because it has no other way to come back. Okay, so it has to stop and reverse its direction. So definitely the velocity is going to become zero. And even if it crosses that horizontal point and goes to the upper half of the circle, there's no chance of it falling into the circle. So there also it has to stop and then come back along the circle itself. Fine. Had there not been the inner surface, okay, I'll show you the diagram on the right side. Consider something like this. Had the inner surface not been there, then what will happen? It has a possibility of falling into the circle. And if there is a possibility of falling into the circle, we proved mathematically that velocity cannot become zero anywhere in the upper half of the circle. So it'll become too slow and then falls off like this. It doesn't stop along the circular path. Okay, it just goes out of the circular path. In fact, we should properly say it goes into the circular path, but it doesn't stop. But if there is no chance of it falling into the circle, then it can stop. Okay, because as it ascends, it keeps losing its velocity. At some point, it will have to come to rest. Now, what we want, okay, what the question is asking is, how much minimum velocity should you give it at the bottommost position such that it reaches the top? Because once it reaches the top, after that, it will roll down on the other side. It will slide down on the other side. So upon reaching the top, the velocity should approximately be zero. That's the condition. So we know velocity at one point. We need velocity at another point, and we know exactly from where to where the object is going. So we know kind of the change in arrangement or the displacement is known to us. And one of the velocities is known, another velocity is asked. What are the different approaches we have, or what are the different methods we have to solve problems like this?
Conservation of mechanical energy, sir.
If you are sure that non-conservative forces are doing zero work, you can apply mechanical energy conservation. Okay, Vanilla, you only tell me, as the ball ascends, what all forces act on it?
Weight and normal, sir.
Weight and normal force. Actually, if you see, there are two surfaces with which the ball can be in contact. See, if the ball is moving fast, what happens is it will have a tendency to go out of the circle. When it has a tendency to fall out of the circle, it's the normal force from the outer surface that acts on it, kind of like this. So maybe when the ball is here also, it's moving fast, it has a tendency to go out of the circle. Normal force from the outer surface will be acting on it. Now, at one position, like see in the lower half, it has no chance of falling into the circle. It will always tend to fall out of the circle. So anywhere in the lower half, normal force will be exerted by the outer surface only. But when it enters the upper half, had the inner surface not been there, it would have, like when it becomes too slow, it has a tendency to fall off into the circle like this. When it has a tendency to fall into the circle, outer surface won't be exerting any normal. It will be losing contact with it. But it now relies on the inner surface. So then the normal force will start acting this way. Situation is like this now. inner surface will start exerting the normal force, because now the ball will be taking support from the inner surface. Fine. In fact, I can even ask you this question. Find out the position where the ball neither takes support of the outer surface nor the inner surface. Exactly the position where exactly normal force is 0. That also you can find out. So till then, it will be taking support from the outer surface. After that, it has a tendency to fall inward. Then it will take support from the inner surface. Okay. Both exerting will not happen because the ball is free to move in that tube. It's not being compressed by the walls of the tube. Okay. If it is being compressed, then both outer wall and inner wall will exert normal force. It's not like that. The ball is moving freely only. So yeah, this is the situation. And as Rishi said, that's the mathematical condition that you'll write. Velocity upon reaching the top is approximately equal to 0. And as Vanilla said, you can, okay, she said we can apply energy conservation, maybe mechanical energy conservation, but we have to check the condition, check if the condition is satisfied or not. As I said, non-conservative forces should not be doing work. And she said that as the ball ascends, the forces acting on it are weight and normal force. Now there could be normal force from the outer surface, there could be normal force from the inner surface. But irrespective of which surface is exerting the normal force, the displacement of the ball is always perpendicular to the normal force at every position. Therefore, normal force in this case will not do any work. Okay, so work done by normal force is 0. The only other force acting is gravity. Let it act. It's a conservative force. So mechanical energy conservation will be valid. Use it, all of you, and derive the speed required at the bottommost position to get to the top. Apply mechanical energy conservation carefully. I'll give you all 2 minutes. Okay, Vanilla, the answer you gave is correct only. Rishi, can you tell how you are applying mechanical energy conservation here?
Sure, so we have to find so it'll be mgr.
Wait. This is how we apply mechanical energy conservation. What kind of potential energy are we supposed to consider? Gravitational or elastic?
Gravitational.
Gravitational. There's no spring involved here. What is the formula for gravitational potential energy when you are applying mechanical energy conservation?
mgh.
So did you assign heights? Where did you take the 0 height as?
The A.
Okay, at point A, you are assuming the height is 0. Okay, let's take h1 as 0 or h initial as 0. Then how much will the final height be?
2r.
2 times the radius. So now tell me, how much is the initial gravitational potential energy based on these heights?
mg2r.
Initial. Where was it initially?
Oh, 0. mg0, so 0.
0. Kinetic energy, how will you write?
Half mu square.
Half mu square. U is what we need to derive. Okay. When it gets to the top, how much is its final kinetic potential energy?
mg2r.
mg into 2r, correct. And kinetic energy?
Half mv square.
How much is v?
But it's nearing 0.
Close to 0. So we'll take it as 0 for the minimum case. That's all. M gets cancelled. 2 goes to the other side. You get u square is equal to 4gr. So you just need to give a speed of under root 4gr for it to get to the top and roll down from the other side. Actually, a speed slightly greater than root 4gr is needed, but you can't tell the number immediately next to a given number. Like suppose root 4gr comes out to be 20 meters per second. You can't tell the number which is next to 20, immediately next to 20. So you'll say minimum required is 20 only, and it's mathematically valid to say like that. Okay. So basically this is also motion in a vertical circle itself, but here there's no chance of the object falling into the circle or out of the circle. then you can directly apply mechanical energy conservation. When it has a chance of falling into the circle, you have to use tension or normal force equation. Like if it's like that Hot Wheels track based question, you have to write normal force as a function of theta. If it's that string and bob based question, then you'll have to write tension as a function of theta. It will be the same. Okay. Fine. So I think this much is enough about motion in a vertical circle. Let's solve some more problems based on mechanical energy conservation and all. Just a moment, I will take the diagram of a spring. Okay, we can use this. Okay. Consider a situation like this. Simple spring block system. And assume there is one more block. Or wait, let's make this one bigger. Bigger one's mass, let it be 2m. Spring constant is k. Surface is smooth. Initially, the spring is at natural length. Assume the block of mass m is moving towards the block of mass 2m with an initial speed, say u. Somehow we gave it that velocity and it is moving towards the block. Okay. Think carefully and one of you tell me what is going to happen. What are the possible things that could happen to this system?
So after a point, it will make contact with the 2m.
Yes, small m collides
ma-
with 2m and then?
Then after that, it'll apply pressure and the spring will get compressed.
Okay, 2m compresses the spring. Okay, what about small m? What could happen to it once it collides with 2m? What are the different possibilities?
So it either stops right there because it couldn't put more force,
Okay.
or if it's like fast enough or something, it'll bounce or something. That'll go front and come back.
So after striking the 2m, it goes back, you're saying?
Yeah.
Okay, that possibility is there. There's another possibility also. After striking 2m, it could continue in the forward direction. Okay, that could also happen. Now, I'm sure you all must have played caroms at some point. Now, when a coin goes and strikes another coin, it's not necessary that the first coin stops or definitely comes back. It's possible that both of them go forward also. Yes or no? When a coin A goes and collides or strikes a coin B, isn't it possible that both of them move forward?
Yes.
That possibility is there. Vanilla, do you agree with that or not?
Yes, sir.
Okay. Okay. So upon collision, there are different possibilities. So suppose you are told that the block of mass m comes to rest after colliding with 2m. And the question is to calculate the maximum compression in the spring. How can we do this? Like, when M goes and collides with 2M, 2M will definitely start moving. And when it starts moving, it starts compressing the spring. But as the spring gets compressed, it starts exerting an opposing force on 2M. So 2M slows and stops somewhere. Let's visualize that situation also, where 2M is coming to rest. So upon collision, like after collision, not upon collision, M comes here, strikes 2M, and as given in the question, M comes to rest after striking 2M. So 2M starts off with some velocity, but as 2M moves forward, the spring gets compressed. Spring starts exerting a force on 2M to the right. So because of the force acting on 2M to the right, okay, let's visualize it step by step only. Where was the natural length of the spring? Natural length was at this position. Now it has crossed that position. So since the spring is compressed, it starts exerting a force on 2M. Now the force will not immediately stop 2M because spring has to be compressed by a sufficient amount to exert enough force. Or the momentum that 2M has, it will reduce gradually. Okay, spring force is not an impulsive force. It cannot exert a large force at natural length. Okay, so gradually the block of mass 2M will slow down, and eventually what will happen, not eventually, I think after that also the motion will be there, but we are going to consider only till that point. Just a moment. So 2M is still, like in that earlier position, 2M is still moving with some speed we don't know. And if it's still moving, then the spring compresses a little further. And if the spring compresses further, spring force will increase further. And due to spring force, 2M will have to stop somewhere. That's what we call as maximum compression in the spring. So these are the different stages. This maximum compression is what you are asked to calculate. So why won't the spring compress? Why won't the spring get compressed any further? Because by then the velocity of 2M has become 0. Now what is there to compress it any further? So this is what is going to happen. I think it'll be better if I put all these together. You know the problem. You have to find out the maximum compression in the spring. So tell me what can be done. Come up with some ideas. Small m comes to rest. Okay, 2m keeps moving. You can call them as v1 and v2 if you want. And as 2m keeps moving, it keeps losing velocity, and gradually it will stop somewhere. Where it stops is what you need to find out. So any idea what can be done?
Well, we can first calculate V2 and then apply work energy theorem.
Okay, so what Vanilla is suggesting is after m goes and collides with 2m, we'll find out the speed with which 2m starts moving. And after that, we'll apply work energy theorem. Why can't you apply directly? Why should you find out the speed with which 2m starts moving?
Because when we find the amount of speed, then we'll get to know which case works for it.
No, see, what is work energy theorem?
Final minus initial.
Yeah, Rishi, it's a very vague answer that you have given. What final, what initial? Tell the theorem properly. What is work energy theorem?
So Work done by all forces equal to change in kinetic energy.
Okay, correct. Work done by all forces is equal to change in kinetic energy. Now in this process, okay, work done by all forces is equal to change in kinetic energy of the system. Okay, you can apply work energy theorem to a system also, not just a single object. Now, one of you tell me, the blocks collide and then the spring gets compressed, all that is fine. What are the forces doing work in this whole process?
Force, sir.
Spring force. Okay. Then can't you write work done by spring force is equal to change in kinetic energy directly from stage 1 to stage 3 without considering stage 2? Because basically what happens, understand this, block of mass m is moving initially, 2m is not moving. Okay, I'll mention that also. 2m is at rest initially. Now mass m goes and collides with 2m. M is coming to rest. 2m starts moving. So you said we will apply work energy theorem after that. So basically what you want to try is work done by spring force is equal to change in kinetic energy of 2m. That's what you suggested doing. What I am asking is the change in kinetic, okay, the kinetic energy gained by 2m due to collision, is it equal to kinetic energy lost by m in the collision? If it is so, okay, if this is correct, then we can directly write work done by spring force is equal to change in kinetic energy of the mass m. Okay, directly from first stage to third stage we can apply. So my question now is mass m giving all its kinetic energy to 2m? Is there a way to confirm that? We know it's losing all its kinetic energy because it was moving with a speed u initially, and then it's coming to rest upon collision. So it's definitely losing all its kinetic energy. Is 2m getting all of that or not? That's the question. Okay. Vanilla, you suggested finding the velocity of 2m first and then applying work energy theorem. Tell me an idea now. How will you find out the velocity with which 2m starts moving? Is there a way to find out the velocity with which 2m starts moving? Okay, listen all of you. Basically what is happening here, one block of mass m is going and colliding with another block of mass 2m. One object is disturbing the motion of another object. Tell me, what principle of physics can be applied when the motion of one object disturbs the motion of another object in a system? We had done collision-based questions before also. What principle of physics can you apply in that collision?
The conservation of linear momentum.
Good. Conservation of linear momentum. That is what we will do to find out the velocity with which 2m starts to move. Okay, let us discuss this point also. Is 2m getting all the energy lost by m? If 2m is getting all the energy lost by m, then you can directly apply work kinetic energy theorem from the first stage to the last stage. But there is no guarantee that 2m gets all the energy lost by m. And we will prove it using conservation of momentum itself. So let's go through this carefully, step by step. First, small m is colliding with 2m, right? So before collision, only small m is moving. It carries some momentum with it. After collision also, let us visualize. It's very important to imagine what is happening. So this is before collision. And let's say this is just after collision. Just after collision, small m will be near to m, but small m will now be at rest. Okay, mass m will now be at rest. Okay, I'll write it as V1 is 0. 2m takes off or starts with some velocity suddenly. Let's call it V2. This is what happens just after the collision. Later that V2 will decrease and become 0. Okay, but immediately after collision, this is the situation. I can say this one's velocity u2, initial velocity of 2m was 0. Initial velocity of m is known to us. Okay. Vanilla suggested using conservation of linear momentum to find the velocity of 2m after collision, and that is valid. In collisions, you will try to do that. But there's a condition for conservation of linear momentum. Aishwarya, can you tell me when is linear momentum conserved?
So when F net is 0.
When net force on the objects is 0, or the system is 0. Now, whose linear momentum are you conserving? Is it only m, only 2m, or the combination of m and 2m? Whose linear momentum is being conserved or will be conserved? In that collision. You have to think in terms of forces. When the blocks just come into contact with each other, there will be a normal force acting between the blocks. One normal force acts on small m this way. The same amount of normal force will act on 2m the other way, action-reaction pair. And apart from these, their weights are acting 2mg and mg, and normal forces from the surface are acting. Okay, you can call them as n2 and n1. Let it be. All the motion is happening in the horizontal direction, so we'll ignore the vertical forces. They are balanced. Let it be. Horizontally, if you observe, there is a net force on m. This normal force is a net force acting on m. So only m's linear momentum won't be conserved. Of course, m's motion is getting disturbed, no? So m's momentum is being disturbed. From initially it was moving, it had momentum, it comes to rest. So its own momentum is getting disturbed. 2m's own momentum also will get disturbed because there is a net force acting on it. But if you consider m and 2m as a system, okay, together, then okay, you all only tell me, how much is the net force acting on this system as a whole? There's one normal force to the right, one normal force to the left. Then how much is the net force acting on it?
0, sir.
0. Okay. So it is the m and 2m system, m and 2m systems momentum, which will be conserved. This system will experience 0 net force. Now, some of you may say, sir, there is a spring, but the spring is initially at its natural length. So it won't be exerting any force at that moment. Okay. So when the collision is happening, spring is not exerting any force. So you can ignore it and apply linear momentum conservation. Using or doing that, we can find out the speed with which 2m starts to move. Okay, let us do that first. After that, we can tell how much the spring will compress, because it is 2m's energy which gets stored in the spring. Okay, after that, we'll apply work energy theorem, mechanical energy conservation, whatever is applicable, we'll try. But let's do momentum conservation first. Momentum is a vector quantity, keep that in mind. And one of you tell me, how much is the initial momentum of this system of m plus 2m combined? Rishi, you tell me, how will you write the momentum?
Our momentum is mv, so it'll be
Which mass is moving?
sir, the 2m one. You know.
Before collision, which mass is moving?
Oh, m, sir.
And with what velocity is it moving?
U.
Which way?
What's the left?
So how will you write initial momentum? Vanilla, tell me how much is the initial momentum of the system?
Mass into initial velocity, sir.
Okay, so it will just be mu. It is to the left, so minus I cap. Momentum is a vector quantity. The other object didn't have any momentum. 2m didn't have any momentum initially. So total initial momentum is minus mu I cap. Rishi, is this clear?
Yes, sir.
Okay. After collision, it is given to you in the problem that m comes to rest. So 2m is the only one which has velocity. Aishwarya, you tell me, how do we write final momentum of this system? We assume 2m is moving with a velocity v2. So tell me how to write the final momentum expression.
Sir, minus 2mv2 I cap.
Correct. 2m is the only one which has momentum finally, and it's moving with a velocity v2 in the negative I cap direction, so minus v2 I cap. Therefore, final momentum is minus 2m v2 I cap. The other particle's momentum is zero. The other object's momentum is zero. M is not moving. Okay. And we know in this process, linear momentum is conserved. Therefore, equating them, minus mu I cap is equal to minus 2m v2 I cap. I cap minus m can be cancelled. You get v2 is equal to u by 2. So we got the speed with which 2m starts to move. Okay, because net force is 0, we know linear momentum conservation is applicable in this situation. We did that. Now let us try to answer the other question. Whether m is transferring all its kinetic energy to 2m or not. Let's see that. Vanilla, tell me, how much is the initial kinetic energy of m?
Half mu square, sir.
Direct formula, half mu square. Finally, it loses all that kinetic energy and it goes to 2m. We know the speed with which 2m is moving and the mass is 2m itself. So Rishi, tell me, how much is the kinetic energy of 2m after collision? Just use the basic formula. Yeah, go ahead.
Half 2m v2, sir.
2m v2 squared, and v2 is u by 2. Let's square it. It becomes half into 2m into u square by 4. Half 2 cancel. It becomes mu square by 4. What kinetic energy was small m having? Mu square by 2 it was having. But what kinetic energy did 2m get? It only got mu square by 4. Okay, so it didn't get all the kinetic energy lost by the smaller block. So some kinetic energy was lost in this process. Can one of you tell me where that kinetic energy will go? It's not getting converted to potential energy. Don't even think about it because the block's heights are not changing. So it's not getting converted to any kind of potential energy. Where is the kinetic energy going? Or what is it getting converted into? That's the proper way to ask.
Sir, to the string.
What did you say?
Is it going to become part of the string? Will it? Because
Spring.
it's. Yeah, sir.
See, the spring still didn't even get compressed. The spring didn't get anything out of this collision. After the collision, 2m starts giving energy to the spring. Okay, even if the spring had not been there, you would have gotten the same speed for 2m. So imagine the spring is not there at all. Some kinetic energy is lost. Where is it going? Okay. See, when two objects collide, what happens in an everyday situation? When two objects collide, what do you observe?
Sure that they stop moving.
See, they don't always have to stop moving. When one carom coin goes and collides another, will they always stop moving? Not like that, no? But what else do you observe? It's not necessary that they stop moving.
Energy gets
That
transferred, sir.
Yeah, some transfer of energy happened, but all the energy didn't get transferred. So what else do we observe when two objects like dash against each other? Okay, some sound,
Explosion takes place.
high explosion, some heat could be produced. Not an explosion always, but some heat can be generated, some sound can be generated. So that is what kinetic energy is getting converted into. It's getting converted to other forms of energy, which are not mechanical energy. Okay. So maybe sound, heat. Usually we say heat. Okay. And see, this loss of mechanical energy can happen only due to non-conservative forces. So there may be some non-conservative forces acting between the blocks. We don't know. And in fact, in this chapter itself, we will learn types of collisions between objects. There you'll understand exactly how two colliding objects may lose kinetic energy permanently. Okay, you learn in this chapter itself, but you should, like from everyday experience, we can tell that the kinetic energy which the small block had could get converted to heat, sound, such other forms of energy. So all the energy possessed by M is, or not possessed, all the energy lost by M is not given to 2M. So the approach that I suggested, that is applying work energy theorem directly from the first stage to the last stage, is not valid. Because in between, there are some non-conservative forces getting involved and doing some work, and we don't know how much work they are doing also. We don't even know the expression for the force. How will we calculate work and apply work energy theorem? So directly before collision to compression of the spring, you can't apply work energy theorem. The theorem is valid, but we don't have expressions to apply it. Nor can we apply mechanical energy conservation directly from the first stage to third stage. Because when two blocks collide, there are some non-conservative forces doing work there. They are causing a permanent loss of mechanical energy from the system. So obviously mechanical energy is not conserved all the way from the first stage to the last stage. Okay. So first for the collision, we'll apply, the only thing we can apply during collision is linear momentum, this kind of collision. Okay. Linear momentum conservation. We do that. We find the speed with which 2M starts moving, and that we have done. So now let us consider the compression of the spring. We know how 2M starts to move. After that, what is left is the compression of the spring. Now you don't even have to consider M anymore. Okay, 2M starts to move with a speed U by 2. We have proved that. We have derived that. And forget all this now. The spring, when 2M just starts to move, the spring is at natural length. It's not compressed, nor is it elongated. After this, the spring starts to get compressed, and you know what happens next. The block slows down, stops somewhere. Let's imagine that part of the motion of the system now. 2M started with a speed U by 2, but it won't maintain that. It cannot maintain that speed. Okay. So as the spring gets compressed, 2M loses that speed. It slows down, stops somewhere. Where it stops is what you are asked to find out. So 2M's velocity is now becoming 0. The compression in the spring is what we need to calculate. Tell me, how can we do this part? Aishwarya, can you suggest any idea? Spring was at natural length, 2m was moving, but gradually 2m comes to rest, spring gets compressed. You should find out how much the spring is compressed. What can be done? Rishi, what do you suggest? Okay, Vanilla, you are saying something?
Work energy theorem, sir.
You want to use work energy theorem? Can be used. We know the initial speed of 2m, u by 2, and we know the final speed 0. So we know the change in speed means we know the change in kinetic energy of the object. And the only force doing work, actually all forces acting on 2m, if you consider, there is a weight, there's a normal force, and as the spring is compressed, spring force will act. Weight and normal force are vertical, motion of the block is horizontal, so they won't be doing any work. The only force doing work is spring force, you can write, and spring force includes the compression in it. Work done by spring force includes compression in it. So that's one way to get the answer. Another way is mechanical energy conservation from here onwards. Once 2m starts compressing the spring, you can apply mechanical energy conservation because spring force is the only force doing work on it, and spring force is a conservative force. Okay, so what we'll do is initial potential energy in the spring plus kinetic energy of the block is equal to final potential energy of the spring plus kinetic energy of the block. Here, the block is moving horizontally, so it's not going up or down. Gravitational potential energy need not be considered. How much ever gravitational potential energy it had initially, the same value it will have finally also. The block is moving on a horizontal surface, so gravitational energy need not even be considered. It will be the same on the initial side and the final side, so it will get cancelled, need not write. But there's a spring force involved, so spring potential energy has to be considered. Rishi, tell me, when the spring is at natural, or tell me the formula for spring's potential energy.
Sir, is it Kx?
Kx is spring force. Okay, Aishwarya, what is the formula for potential energy stored in a spring?
Sir, half Kx square.
Okay, fine. Use this and tell me how much is the initial potential energy in the spring when it's neither compressed nor elongated. In half kx square, what does x stand for?
Elongation or compression.
Elongation or compression in the spring. Correct. When it is at natural length, it is neither elongated nor compressed. So initial potential energy stored in the spring is 0. And the block had kinetic energy. Half into its mass is 2m. You need to be very careful. Speed is u by 2 and you square it. So the total initial mechanical energy becomes mu square by 4. Finally, the spring is compressed by some extent. So the spring's potential energy will be half kx square. We don't know x. But the block has come to rest finally. So the final mechanical energy will be half kx square. Now we just need to equate this. Initial mechanical energy is equal to final mechanical energy. Therefore, mu square by 4 is equal to kx square by 2. And from there you can get x. That's the maximum compression in the spring. That part you can do. So let's go back to the original question that was asked. A block was connected to a spring and that system was initially at natural length and at rest. Another block came and collided with this one, due to which this system got disturbed, and you are asked to what maximum extent the spring gets compressed. So understand how we went towards the solution. Okay, what steps we took to solve this problem. First thing is imagination. Okay, not just this problem, any physics problem, especially mechanics. If you want to solve correctly, you should visualize what happens. There was some hint given in the question. Block of mass m comes to rest after colliding with 2m. So we visualize that m goes and collides with 2m. then M dashes into 2M, no, it exerts a force on it. So 2M starts to move. M stops, 2M starts. Thereafter, the spring gets compressed. So that's the imagination part. Now the physics. In collisions, you can apply linear momentum conservation, but still we checked if net force is 0 or not, and we were sure that the net force is 0. We applied linear momentum conservation. You can't apply mechanical energy conservation during collisions directly. Okay, as of now, you don't even know the type of collisions and all. So don't even think of applying mechanical energy conservation during collisions, because when two objects collide, like we don't even know what are the exact forces acting there. Okay, or what are the exact forces doing work there. We'll discuss that in this chapter itself, but as of now, we don't know. So you can't say mechanical energy conservation can be applied for collisions. And you cannot apply work energy theorem for a collision also, because you can't write an expression for work done by those forces involved in the collision. Work energy theorem is always applicable, but you can't write an expression for it during collisions. Okay, that's the problem. So as of now, the only thing we can do or we can apply during collisions is linear momentum conservation. We did that. We found out the speed with which 2M moves. And we even found out if 2M is getting all the energy lost by M, and we see that it's not getting all the energy lost by M. Okay, so had you applied energy conservation, you would have made a mistake. Should not do that during collisions. After collision, 2M compresses the spring. For that process, mechanical energy is conserved, because spring force is a conservative force. The force that acted between M and 2M when they dashed into each other, we don't know whether it is conservative or not. Okay. And in fact, our calculations proved that it is non-conservative. Some kinetic energy was permanently lost during that collision. So whatever forces acted between the blocks during collision must have been non-conservative. Okay. At least some of them must have been non-conservative. They caused a loss in mechanical energy of the system. Okay. So based on this, I'll give you another question for practice. Just solve it in reverse. Okay, I'll send you the worksheet tomorrow. Solve it in reverse means a compressed spring will be there, will release the block. So the compressed spring will push the block, and then that block goes and collides with another block. You have to find out what happens. Can do that. And you may be asked questions like this also. Block suspended from a string. A bullet goes and strikes the block. When bullet goes and strikes the block, yes, the block could get shattered. That possibility is there. But if the block is strong enough, the bullet can get embedded in the block. Okay, but bullet had momentum with it. When it goes and hits the block and gets stuck inside the block will start moving because the bullet hit the block. So you may be asked to what extent the block will swing. Okay, or you may be asked what should be the speed of the bullet such that the block goes at least till this position. So it's a combination of momentum conservation, energy conservation, concepts of motion in a vertical circle also. Okay. So anyway, I'll give you steps to solve it carefully. But make sure you revise motion in a vertical circle and mechanical energy conservation thoroughly. And solve that today's problem. I'll send you all the notes. You find out where exactly it loses contact with the surface and send the answer back to me. Okay, thank you all. It's getting late. We'll continue on Wednesday.